Okay, now we're on to 2.3, and there's not really like a concept in 2.3. It's kind of just doing these practice problems. So let's just start one. If f of x equals the sine of square root of x, find f prime of 2. And this one you have to use your calculator. Well, at least that's what like the problem is to show you how to find the derivative using your calculator. So on my calculator, you press math, and then it is number 8, nDeriv, and then you press that. And then you can plug in the numbers and solve it in the function. But you can also do it on Desmos. If you do d over dx of sine of x to the 1/2, which is the same thing as square root of x. And then we're trying to find it at 2. At 2, it is 0.055. We can write 0.055 as our answer. 0.055. If you do it on a calculator, I think you'll get 0.05513, which is more specific. But for the calculator, just write the function in and say what value you want it evaluated as. Set math, and then for me it's 8, and I have the TI-84. Okay, this is the next practice problem. It's like the same thing, except this time we're trying to find the line tangent to the function. And so we can do this a few ways. First, we have to find, well, we know the x value is going to be 1, but for a tangent line, and this is the formula for a tangent line, it's y minus y1 equals m times x minus x1, in case anyone forgot. So we need x1, y1, and m. We already have x1, which is 1, x1. And then we're trying to find y1 and m. To find m, we take the derivative, which we can do on our calculator. And to find y1, we just plug in the x value 1. If we plug in the x value 1, we get 1 over 1 plus 1 in the square root, which is going to end up being 0.707. The next thing we're going to do is find the derivative to find m, and with our calculator. So I'm just going to go to Desmos real quick and write the function in. And then we're trying to find it at x equals 1. X equals 1, it is negative 0.177. So let's write that down. And then we have the line tangent to the function. Let's write it down. Y minus 0.707 equals negative 0.177 times x minus 1. And that's the line tangent, or the tangent line. Okay, for this section, the last type of problem you're going to see is the table problem. You're going to get the x and the y values. It's going to ask you to estimate the rate of change at a specific spot. In this case, it's f prime of 3. So, how do we do this? So, since it's at f prime of 3, we look at well, there's no specific spot at x equals 3. That's number one. You got to see that. Then we look at the points around x equals 3, which in this case are 4 and 2. So we can use those points to estimate the average rate of change at x equals 3. So pretty much you use the slope formula, but you use it for these 2 points around 3 in order to get the average slope. So in this case, you do 10 minus 3 over 4 minus 2. Since 4 and 2 are are next to 3, and these are the y values that correspond to them. So you get 7 over 2. So f prime of 3 is approximately 7/2, because that's what the rate of change between the 2 points is that are next to 3. And that's how you do a table problem. Make sure you label your answer, because most of the time they're going to ask for it. So in this case, it'd be miles per hour. Miles per hour. That's how you do it. Okay, now we're on to 2.4, and this isn't really like a math thing either, it's a concept. It's talking about differentiability. And to be differentiable, it means you can take the derivative of the function at any point. But there are special cases in which you can't take the derivative, and I'm going to draw those right now. Okay, a function is not differentiable at a certain spot if there's a hole in the graph. If the function is discontinuous of a sort, so hole, or you can have like this, where you have a point up here, but there's a jump. This space in between is empty. If there's discontinuity in the function, that means you can't take the derivative in that spot. Okay, then the next thing you can't take the derivative of is a corner or a cusp. So a corner is like this, where like two straight lines meet, and they're kind of like perpendicular to each other. So you can't take the derivative here because on either side the rate of change is completely different. So it makes no sense to how you could take the derivative here. And the other thing is a cusp, which is the same thing really, but it's more rounded. And in these spots you can't take the derivative. Lastly, you can't take the derivative of something if it looks like this, if it's literally a vertical line in the middle, because you end up with the scenario where it's like y2 minus y1 over x2 minus x1, but the x2 minus x1 is literally 0, and we can't divide by 0, so we cannot take the derivative of this. That's pretty much the reasoning for it, and you just got to know that. Alright, lastly for 2.4, you got some true or false. Differentiability implies continuity. Is this true or false? The answer is true, because if it's differentiable, it means there's no hole in the graph, because you can take the derivative of it, and there's also no jump. So none of these. So differentiability does imply continuity. The next one is, does continuity imply differentiability? This one is false. This is because of what we talked about, corners and cusps. This function that looks like this is totally continuous, but it's a corner, so you can't take the derivative of it, so it is not differentiable. Same with the vertical tangent that we talked about. This is continuous, but you can't take the derivative since it is literally straight up. And that's pretty much it for 2.4.